Well, let's get started. I'll just introduce a few things quickly, not to eat into too much of David's time. Hello, everyone, and welcome to the second installment of the post-Bayesian seminar. Here are all of the important links in case you missed them last time. The new one here at the bottom is for our workshop registration. So this is the big news we would like to share this week. So we have now got a website up and running for our workshop. Registration is open, and we're now accepting submissions. This will be sent around in an email afterwards in case you don't have time to snap the QR codes. So today, again, for questions, please use the Q&A function of the chat to ask your questions. If we find some questions that are heavily upvoted, we'll interrupt David's talk and get his view on them. And then presumably after the talk, we'll have some time to talk through everything that's left. So yeah, just to show again the structure we have for this chapter for the seminar, this week we've got David Frazier. So David is a professor at Monash. He's been really instrumental in the development of simulation-based inference and specifically misspecification and forecasting. He's the scientific co-chair of Bayes this year, which I think he'll talk to us a bit more about. And as Jeremiah said last week, he's going to talk to us a bit about the theoretical toolkit we have to handle these new and exciting objects. And having had the privilege of working with David, I can say that I'm incredibly excited for this talk. So now probably I'll hand it over to you, David.
Thank you very much, Jan. I'll go ahead and share my slides and then go ahead and get this show on the road. So first of all, I want to thank both Jeremiah, Jan, and Matthias for organizing this chapter and also for inviting me to give a talk. It's quite a privilege, especially after such a foundational kind of lovely lecture that Jay gave 2 weeks ago. It's going to be a bit hard to follow, but I'll do my best, especially given that the topic I'm talking about is somewhat more dry in many ways. What I'm really going to be talking about today is the theoretical foundations of what I think of as kind of post-Bayesian belief updates, but really I'm going to focus specifically on Gibbs measures and generalized posteriors in this context. Before I do any of that, though, I want to go ahead and give a quick shout out to BayesConf 2025. If you are going to be if you're interested in Bayesian computation or misspecification in Bayes, then I highly recommend this. So BayesConf is going to run the 16th through the 20th of June. Myself and Leah Price South are the scientific co-chairs, and David Knott is the local organizer for the committee. We also have 2 lovely satellite workshops that are going to take place the 16th and the 17th before the main conference, one of which is actually organized by FX and Jeremiah, along with my colleague at Monash, of Jack Jewson, who some of you may also know. So if you're interested in that, I highly recommend you go. Registration, early bird registration and submissions, submission ends the 28th, and then early bird registration will finish the 15th of March. So go ahead and get in there if you're interested in coming to Singapore. Right, so what am I going to cover? I'm going to cover today kind of the theoretical toolkit, as Jan said, of Gibbs measures and generalized Bayesian belief updates. Now, first of all, I'm going to have to define those things, but that's really just going to be the set notation. There are many different types of results you could talk about. I'm going to talk about what I see as kind of the 2 most foundational. The 2 most foundational to me are kind of posterior concentration, and there's a couple of different ways you can actually do this. There's the kind of old school way that I learned it, and there's also the kind of what I think of as the new school way of doing it, which is kind of using provably approximately correct Bayes. And the reason I'm not going to cover this, because I think this is in some sense a much more elegant framework than the kind of stochastic limit theory stuff I'm going to talk about, because Pierre's going to talk quite a bit about this, and indeed a lot of his chapter of this post-Bayesian workshop is on Pac Bayes. So I'm not going to steal his thunder at all. I'm going to leave all that to him, who's definitely the expert on it. After we move on from talking about concentration, I'm going to talk about coverage and posterior asymptotic normality. These 2 things are going to kind of go hand in hand. I'm going to try and interweave them to show you why they go hand in hand. And the last thing I'm going to kind of cover is I'm going to interject a few examples, what I think of as applications of where this theory can be useful. Right. So this talk is really based on what I think of as kind of 4 key papers in the literature and 2 kind of applications of these general theories. The 2 key papers I think of on concentration, where they kind of spell things out in a very lovely way. And if you are interested in this literature at all, these are the papers you should read. There's this paper from Nicholas Searing and Ryan Martin and Bernoulli, and I've just given the archive links to all these because they're persistent, which really gives a lovely overview of posterior concentration in Gibbs measures more generally. And then there's this cool paper from Pierre and James Ridgway in Annals, where they talk about this kind of new school way of showing it. Now, in terms of asymptotic normality and kind of Bernstein-von Mises phenomena we're going to talk about, really the best paper you could ever hope to read on this was written by Jeff Miller in JMLR in 2021, where he just goes into gory detail about how these things work and gives you line-by-line examples of how to get your teeth around these things. I cannot tell you how many times I've referred back to that paper. It's exceptionally well written, and I thank Jeff for writing this paper every time I see him. So the other very nice paper in this respect is also this handbook article from Ryan and Nicholas, which I think is now a handbook of statistics. In terms of applications of the theory, it's really around some work that Jeremias, Edwin, and Jan and I have done around prediction with these Gibbs measures, and some work that Jeremias and I have done along with some other collaborators on what happens when you have to estimate the loss function here. Right. So let's go ahead and move on to our main topic, which is let's talk about Gibbs measures at first, or generalized Bayesian belief updates. And before I show these, I want to think about the connection that exists between these generalized posteriors in some sense, or Gibbs measures, with standard Bayes. In the case where the data is IID and you kind of have a nice simple likelihood model here, p theta of x, well then we all know that our posterior, our standard Bayes posterior, is really nothing but the product of the likelihood and the prior normalized by the normalizing constant given here. Now, the kind of beautiful representation of this that we're going to use quite a bit, and we use quite a bit in the theoretical construction of these objects, is that representation of that object as the argument minimizer of some infinite dimensional program over the space of measures on theta, which is this script p theta here. And that's useful because basically what you can show is that the solution of that problem has the form of the Bayes posterior if you take as the loss of that problem minus the log loss, or you take the KL divergence between your sample and your p theta. I think Jay talked quite a bit about this, so I'm not going to spend too much time on this. But this is this kind of optimization-centric view of Bayesian inference. The first result I know this explicit form comes out is actually an old paper from Arnold Zellner in The American Statistician in the 80s, where he used this formulation to show that this is, in a sense, why Bayes processes information optimally. Now, from here, you might think, well, if this is what Bayes gives us, what happens if I choose a different loss function? When you choose a different loss function, in general, you're going to get what we refer to as a Gibbs measure. So if I now move from a likelihood loss, or a kind of a log loss, essentially a log of a likelihood, but now I just have some arbitrary criterion function, dn of theta, well, then I'm no longer going to have my Bayes posterior, I'm going to have a Gibbs measure. And that Gibbs measure looks exactly like the likelihood loss, except now it's kind of no longer a standard posterior, it's something that depends on the loss you choose. In the case where the losses take the representation as summable increments here, this dn theta as a sum, well, then this is exactly what Basiri, Walker, and Holmes called a generalized posterior. Different choices of D essentially give you different inference vehicles, is the way I like to think about them. They're essentially not just different belief updates, they're heading you in very different directions. They're heading you in different directions because what is big and what is small in one loss is necessarily different from what is big and small in another loss. And essentially, if you look at this loss problem here, you're essentially trying to look for measures that minimize the average value of that loss, subject to the KL condition. So given that this Gibbs measure has no relationship to a Bayes posterior in a general context, we really need to take a step back and go, are these things actually reasonable even to use? And to me, reasonableness, the only way I can really think about that, given the general form that this thing has here, is with asymptotics or with theory. I need to try and say, what's the behavior of this object on average, or in high probability, or in terms of some expectation? Why, might you ask, I care about this? Well, in general, I don't know what sort of behavior this thing's going to have, but I know that this standard Bayesian posterior has very good large sample behavior in terms of its concentration and in terms of its asymptotic normality. there are various regularity conditions and stuff that are going to say that this posterior, the standard posterior, is good in some sense. And really, if I want to say a similar thing about the Gibbs measure, I need to explore the similar behaviors. And those two behaviors are going to be the concentration of that posterior. As more data accumulates, where does it accumulate mass? And how that mass accumulates, which deals with the shape of that posterior. Roughly, you would hope that in large samples, this thing is roughly Gaussian, because that's going to mean we can get a handle on its credible sets, we can figure out its repeated sampling behavior, and how reliable those inferences are. When here reliable, we think of in terms of credibility in the kind of sense of Rubin in his kind of early annals papers on thinking about how reliable is Bayesian inference. Right, so the simplest of or the kind of stepping stone in any theoretical analysis of Bayes is really going to be starting with posterior concentration. It is in many ways the most basic property one could ever want of a posterior. Basically, what concentration means is as more data becomes available, your inferences become more precise. I have a funny little plot here showing just a standard Bayesian posterior based on a likelihood in comparison to the prior. As I observe more and more data, as you observe more and more data, you see that this peak of this posterior tends to increase, and they're all around the same value. In this case, there's a true value, and that true value is 1 because I generated the data, I get to play God. And I know that this thing is concentrating around the true value of 1. And roughly, if I look at it, it roughly looks Gaussian. And this is kind of going to be the flavor of what we're going to want here. This is well and nice, and it's a nice intuitive idea about what you want these posteriors to operate on. As more data becomes available, you want more precise inferences, but on what point? If I'm working with Gibbs measures, there's no such thing as a truth. Instead, what we have in Gibbs measures or generalized posteriors is a population loss minimizer. So this theta star is defined as the argument minimizer of my expected population loss. And the hope, if you kind of take a parallel with the standard Bayes posterior here, which is going to concentrate on the true data generating process if one exists, you would hope that your Gibbs measure or your generalized posterior is going to concentrate onto that loss minimizer. And to formalize this, I need to start introducing some math. Basically, what we're going to say here is that the Gibbs posterior is going to concentrate around that loss minimizer at some rate, and that rate we're going to call epsilon n with respect to some metric, if the posterior set containing values of theta, not containing values of theta far away from theta, goes to 0 on average. Now, one way to think about this quite intuitively is that if I have a ball around the truth, to negate this definition and to say, if I have a ball around the truth, all its mass around that ball must go to 1. So essentially, my posterior is going to look like all of its mass on a ball around the loss minimizer. And the rate at which those balls contract is called the concentration rate. That's essentially all this definition is saying. This MN is a technical device that allows us to work out the rate of concentration depending on certain, and it's a kind of a hyperparameter that we can play around with in the math to make the rate of concentration nice or not nice. Why should I care? This is kind of going to be a theme of this talk. I may have spent a lot of time doing this stuff, but I know this can be quite dry and boring for lots of people. And so I'm going to try and impress upon you, the kind of non-theoretician possibly, why you should continue listening to me babble on. The first is that this definition, while seemingly innocuous, actually contains a wealth of information. It tells us not only how fast our posterior concentrates, but it tells us the relationship between the loss and the prior. It tells us what sorts of conditions we need on the loss in order to obtain fast rates of convergence or slow rates of convergence. It tells us what conditions, what choices of prior, therefore, we need in order to obtain faster rates of concentration. So for instance, in the very canonical simple case, I have a parametric model, no dimensions increasing, just fixed. Everything is very simple, classical statistics 101. Then your rate of concentration should be the canonical rate. Generally speaking, it should be 1 on the square root of the sample size. However, if the number of parameters is increasing as the sample size diverges, then you're going to get a slower rate. Why are you going to get a slower rate? because the very nature of those balls I'm using to define that thing, right, to define this posterior concentration, are increasing because they're scaling up as the dimension increases as well. Now, what this basically tells you is that there are good priors and bad priors. If I have a really bad prior, I can have slower rates of concentration. If I have a good prior, it's going to be okay. Now, it just so happens that in the parametric world, a lot of us operate, the choice of prior is largely irrelevant because so long as I have full support, I'm going to kind of be okay. So what does concentration actually look like? So this is a picture that Jay actually used in his talk 2 weeks ago, and I went ahead and ripped it because it was exactly what I wanted to show. Here's this kind of safe Bayes paper from Grunwald, and I think this might actually be the Grunwald Van Omen Bayesian analysis paper, if I remember correctly. And what you kind of see is you see basically what they're plotting here is the squared risk of different types of posteriors for a regression function. And this underdashed line here is the true model. And what you can think of these different lines as being is actually just different choices of this learning rate, omega. So they're actually, each of those lines essentially represents a different omega on that slide. And what you see is that for small sample sizes, really less than, say, 300 in this context, you get very different behaviors in terms of that squared risk, i.e. the posteriors that come out of that and the predictions they make in terms of the regression function are very, very different. But as the sample size gets larger and larger, regardless of the learning rate I choose, it doesn't really matter. This is because the posterior is concentrating. And for any fixed value of that learning rate, the concentration is going to wipe it away. It doesn't matter so much. Here's a particularly interesting example of this, which is also a safe Bayes paper from Grunwald, and I forget who his co-authors were. In this case, this is safe Bayes for GLMs or something. Here you have the loss of probability classification, right? Ones and zeros, Bayesian linear regression, Bayesian logistic regression, probability of y equal 1 given the x's. And what you see here is that if I just do standard Bayes, I can be very far off in terms of this risk for small sample sizes. Again, small sample sizes on the x-axis, the risk is on the y-axis. And what you see here, if I'm doing standard Bayes, well, then I have a relatively large risk at small sample sizes. If I'm doing gen Bayes, I have a smaller risk based on a particularly chosen learning rate. Now, what you again see there is around 300, the difference between those two risks is very, very small. And if you were to go out to 3,000, they would lie on top of each other. And this is all because the posterior is concentrating. So in other words, even if you aren't so concerned about the idea of concentration, at least what this is showing is that there's a usefulness for studying it because we can think about things like learning rates, for instance. But really, from a more general perspective, you might care about when your posterior is going to concentrate versus when it's not. And really, what you can kind of work out from reading this literature and living this literature is that there are two key conditions you need to be satisfied. And I'm going to call these conditions the prior mass condition, and I'm going to make up a new name called the well-behaved loss condition. And I'm going to use the second condition to try and connect a bit of Bayes and exactly some of the existing concentration stuff on Gibbs measures. But first, I want to talk about the prior mass condition because in many ways, it's the better understood of the two conditions. Basically, what the prior mass condition requires is that for certain sets Bn, and I define those sets Bn here, basically they're balls containing the loss difference and something that operates like the variance of the loss difference. And here it's the maximum of the two. If the prior on those balls can be lower bounded by something that looks exponential, then you're fine. Basically, what this means is that for sets containing the truth, you need at least an exponential mass of those sets. If it's less than that, then there are no guarantees on what's going to happen here. In the case where you have losses that are bounded, so for instance, you have, say, the maximum mean discrepancy, you can throw away the variance term essentially and just look at the loss difference of the expected loss difference between the two. This condition is not so concerning. So basically this condition in various guises has been known in the asymptotics of Bayesian analysis for the better part of 25 years at this stage, really. There's a sequence of very influential papers that are written in the annals in the late 90s, early 2000s, where basically they look at this condition in the context of likelihoods. And basically you can port a lot of that literature directly over to this context. You're just changing the likelihood loss to your chosen loss, right? And what that kind of means is if you can work out those expectations, you're kind of going to be okay. What I find much more interesting to study, at least, is this well-behaved loss condition. basically what we need here, if we think about the structure of the Gibbs measure or the generalized posterior, it looks like exp of minus some constants d are lost times the prior. Well, that's the kernel of the posterior, and then I'm going to normalize by that. Now, you might ask what happens if that normalizer is infinite. If that normalizer is infinite, then my posterior is 0 for all values of theta, and it's ill-defined. So right away, you kind of see intuitively that to have any control on these posteriors, we're really going to need to control something like exp of this loss difference if we're going to have any hope of controlling anything. What that means, essentially, is there's going to be a couple of different ways I can try and control the behavior of these objects. The first, and this goes back to a paper from Nicholas Heering and Ryan as well, is that if the loss has an exponential moment and your data is IID, such that you can kind of normalize that thing by some arbitrary constant, then you're fine. So in other words, if this condition is satisfied, you can kind of squint a little bit and see if I take expectations of that thing above it. Oh, well, then I'm kind of going to be okay. That thing's bounded. And so the normalizer of my Gibbs measure is going to be bounded and everything's going to be hunky-dory. This is kind of a very intuitive version of that condition. A slightly more obtuse version of that condition, but one I've particularly coming to like more and more the more I use it, is this kind of Hofding or Bernstein type condition. This is the condition that they often use in Bayes to try and establish high probability bounds on Bayesian, on Gibbs measures and kind of Bayes bounds. And basically what this says is, well, I don't know that that thing is 1, right? I don't know that that loss difference is 1. What I do know is that it's upper bounded by something like e to the minus n. So that as n gets very, very large, then I'm okay. But it's not necessarily upper bounded at all values of theta. It's only necessarily bounded at those values for which, so it's not even bounded necessarily, but the prior is such that values where that mass starts escaping, the prior kills, which is kind of useful in a sense because it says, look, I can choose a prior that might not be standard, but that kills areas of the loss that diverge, so I can get a well-behaved concentration rate. Now, the other kind of condition you will see in this literature, and one that I've used in some other work, and particularly this work with Jan and Jay, is what I think of as kind of the more frequentist version of these conditions, and is one that kind of Ryan, Martin, and Nicholas Heering talk about in their handbook paper, which is what I think of as the conjunction of two conditions: a uniform CLT at some rate, and then this well-separated maximum, or well-separated minimum in this case. If you put those two assumptions together, you can prove an assumption like that I've written here in the third piece. This looks kind of ugly, but basically all it's saying, if I take exp, if I take minus on both sides, take exp of everything, basically that's a version of the condition I wrote above in probability. I don't really think too hard about how these conditions fit together. They don't fit together perfectly in the sense of one being weaker than the other. Really, the way I view these conditions is if you want to prove concentration in your example, you choose whichever one is easiest to use. I'm not a purist in terms of this. I think these are all conditions that are going to give you the similar rates of concentration, and you just use whatever is easiest. I've just pulled out what I think are the 3 most relatable conditions, essentially, in this literature that you can play around with to try and establish concentration. This is all really kind of well and nice. And if you can establish these 2 conditions, you're going to get a posterior that behaves as it should, in the sense that you're going to concentrate no longer around some true value necessarily like this, but you're going to concentrate around that theta star, which is the population loss minimizer. So you've now escaped the world of truth, which is good because nothing is ever really true. It's all just our views of reality. But what you are going to get is some view of reality, essentially, that's hopefully beneficial for your problem. And that all comes down to how you choose your loss, which I'm not going to talk about, and which no one really has many thoughts of help on, actually. It's kind of one of the problems with this literature is now you've opened Pandora's box, and everything now becomes a valid loss function. Anyway, one of the things I will talk about is everything I've talked about. One of the things I will mention is everything I've talked about so far implicitly assumes that you can calculate this dn right here. Everything I've said assumes that dn is known in closed form, but there are many interesting cases where it's not. Kind of the canonical case I like to think about is maximum mean discrepancy. In the case where your loss is maximum mean discrepancy between the empirical measure Pn and your model-based measure P theta, what you would actually want to compute would be this maximum mean discrepancy given here. The difficulty is the calculation of that relies on two intractable expectations for anything that's even a mildly complicated model. So this is the double expectation with respect to the model of the kernel given that second piece. And this is just the expectation of the kernel function with respect to the model for any given observed data point. Basically, anything outside of exponential families, this is not really feasible to do, or discrete data. So what have some people done in practice? And what some people have done in practice, they said, well, I can't actually estimate these. And there are various frequentist and Bayesian versions of this, so I'm not going to say anything particular. But what they've realized is, well, I can't actually calculate the MMD. So what I do is I sample from the model. I create a new empirical measure based on the simulated data that I've sampled from that model, and I replace those intractable expectations with their simulated counterparts. Actually, funnily enough, the first paper I ever read about this was years and years ago that FX wrote. Would have been like 2018 or something, I think, where they were doing MMD with this estimated law, with their estimated simulated loss. Now that's all well and nice, but if I want to be Bayesian with this and not frequentist, I can try and use this as my loss function. However, what you quickly see is then you're no longer actually conducting inference on data if you do this. What you're actually conducting Bayesian inference on, or generalized Bayesian inference on, is theta and the random numbers used to generate that MMD. That's not particularly helpful, I think, actually, because basically what it means is for any different realization of those random numbers, I would have got a different posterior. So I need to do something with that. And so the way we deal with that is we throw that kernel inside of Metropolis Hastings and we sample from it. But in so doing, what happens is we now no longer sample from that target we initially wanted from. We now end up sampling from some target where I've integrated out those z's. And this is quite painful because now I move from a target that I could easily reason about, and it has this nice form of kind of exp of some loss function. And now there's this nasty integral on the outside, and I can't deal with it. And again, just to say, why does this matter? I want to show you just a very simple short example where we compare kind of the intractable kind of posterior you would want to actually calculate, which is given here by this black curve. And I'll explain exactly what's going on here in a little bit, which is given here by this black curve. And this version, this feasible version based on, oops, sorry, one second. And this feasible version that I've denoted here, which we denote by PM, because basically for those of you who have ever done anything with Markov chain Monte Carlo and pseudo-marginal Markov chain Monte Carlo, you notice that immediately as kind of the kernel of a pseudo-marginal posterior. So what you see here is I'm comparing that feasible target against one thing, the target that was indeed infeasible until we started revising this paper. And what you see is the target depends on the number of simulated samples I'm using, right? So in the case of the MMD, you can think of this M as for every I observation, I'm simulating 2, 50, 10 simulated samples for each N and running that through a Metropolis sampler to get out a posterior. And this is just for a simple bivariate copulate example with rho being 0.5, so not a very strong amount of dependence. And what you kind of see by looking at low values of M, right? So 2 observations for each I in this context, right? So I have 100 observations on the left and 500 observations on the right. So here I'm simulating essentially for each iteration of the MCMC algorithm, 200 data points. I'm then in the purple simulating 1,000 data points, 5,000 data points, right? For each value of the MCMC, which is horrifically wasteful. What you also see is that I require more simulations as the sample size increases, right? So if you think about these numbers increase quite a bit, now I need 50 simulations per individual I to get the chain to even move. If you do anything less, it doesn't even want to move. And what you have here in black is the actual target you would want to sample from. This is actually from an algorithm that we derived very recently. This is a paper that we're revising based on some comments from some reviewers. And we've kind of come up with a way of actually doing this and getting the infeasible target, which is what you see here in black. But mathematically, what's going on here is that if you don't choose the number of simulations large enough, your posterior is never going to concentrate. So for instance, in order for it to concentrate at the kind of canonical parametric rate of root n in parametric models, basically what we show is the only way that's going to happen is if you choose the number of simulations, m, to be of the same order as the sample size, which is exactly what you're seeing here, right? Here, my sample size on the right was 500. And the only way I'm getting something that looks close to the target is where I'm simulating with m equal to n, which means I have essentially n squared simulations at every MCMC iteration, which is horrifically wasteful. Versus the algorithm that we derive, which is kind of nice, and in the sense that it doesn't really, the target's the same regardless of the number of simulations you use. And this really comes out in the theory, and you can show, in fact, under a Bernstein condition on that loss, that you get this concentration not really occurring unless you have the number of simulations equal to the number of observations. So this is kind of a bad thing. And essentially, it says if you're doing generalized Bayesian inference or Gibbs measures with estimated losses, you really shouldn't be using MCMC. You should use the algorithm that hopefully will be out on archive that we have in about a month, hopefully, once the simulations get done running. Okay. So I'm going to go ahead and move on now that we've talked about posterior concentration and kind of shown you some non-standard phenomena of that context. I want to move on and talk more about what other sorts of behaviors we might be interested in looking at. In particular, I want to talk about what would probably be the second most standard of these, which is asymptotic posterior normality or a Bernstein-von Mises phenomena. So concentration is helpful. It's nice. It's kind of a necessary piece. But if I'm working in kind of parametric models, and simple parametric models or certain classes of semi-parametric models, it doesn't really tell me much. It just says that everything's going to concentrate, and the rate at which it's going to concentrate is the parametric rate. I need something more intuitive. I need something more meaningful to sink my teeth into to say, am I going to be as good as method X or something like this, right? Then the question that immediately comes to mind is what behavior should you expect? And to my mind, just looking at this plot of concentration, the phenomena that I should hopefully expect is that concentration, I'll get concentration around that loss minimizer, right, which is this peakedness, but the way it concentrates should be roughly Gaussian. That is, as more and more data becomes available, my posterior should resemble a Gaussian density with a peak that's increasing to zero, i.e. a variance that's going to zero. This indeed is the basis of Bernstein-von Mises phenomena or Bernstein-von Mises theory, which basically says that as more data accumulates, the posterior looks more and more Gaussian around the loss minimizer. This is kind of, I want to take a bit of an aside and give you a bit of a historical lesson in terms of really why BVMs were very useful in some sense. So there's a bunch of old papers in the 60s and 70s that were initially written on Bernstein-von Mises phenomena and posterior normality. And the whole reason it was written is that there was this big debate between frequentists and Bayesians about prior choice. And a lot of BVM theory kind of was developed basically to say that my prior washes out. And eventually the frequentist and the Bayesian will agree, and we all get to hold hands and ride off into the sunset. I would say that this is also a kind of look what I can do idea in the sense that, which is why I have this really bad old Mad TV sketch thing from here with Stewart, if I'm really dating myself probably here. But the idea being that the Bayesian can do everything the frequentist can, but they can get out a nice coherent way of doing it. Kind of look what I can do. I can do not only what you can do, I can do this in a very probabilistic way. I would say this is probably the older view of BVMs. I wouldn't say this is the view anymore. But before I don't want to derive these things. I don't want to say any more about them than I have to in a sense, but I do want to give you the intuition, because really that's going to get you 90% of the way there, of why this happens. And basically why this behavior happens is it all comes from the second order Taylor series expansion of the loss. If I look at a second order Taylor's expansion of that loss function dn around my loss minimizer theta n, and if that theta n sets the gradient of that loss to zero, so that that first term in that Taylor series expansion drops out, you essentially have a quadratic function in theta. If I plug that thing and the remainder term up into the Gibbs posterior, right? If I replace dn theta with dn theta minus dn theta, which is just a transformation. If you divide numerator and denominator of that posterior by 1, you can easily do this. Then you plug that loss expansion, that expansion of the loss into that posterior, and you basically see that what matters is that first term in that posterior. If I disregard the remainder term, and the whole ugliness and meat of these proofs for proving these is essentially proving that you can deal with that thing. That's it. If you just neglect it and say it's fine, it doesn't matter, and you look at that first piece, you see that that's a Gaussian kernel. That's all it is. And so that first piece is essentially a Gaussian kernel where the variance of that Gaussian is determined by the second derivative matrix of the loss function and this omega term. That is, if I were to do a change of variables from theta to root n of theta minus, say, theta star or theta n, then I would get something that was exactly a Gaussian up to the prior. So that up to the prior, my Gibbs measure would basically look like a Gaussian density. So this is strictly, so basically what this is saying is any case where you have you can do a second order Taylor series expansion of your loss, and the remainder term in that expansion can be controlled, Bob's your uncle, you get a BVM. And God bless him, Jeff worked so many examples out in this paper, things like composite likelihoods, quasi-likelihoods, GLMs, Gauss Markov random fields, Boltzmann machines, Cox models. Any case of those, you're going to get a BVM. This is not to say those are the only cases. Many other losses will also satisfy this. You actually don't need this exact expansion. You need something like it, which means this is going to be satisfied under conditions where the loss itself may not have a quadratic expansion, but its expected counterpart does. So so-called equicontinuity conditions will be sufficient in order to derive something similar. So visually, what does this look like? Visually, basically what it means is if I think about my credible sets from the Gibbs measure, basically what it means is that those credible sets for a reasonably large sample size are going to be elliptical because they're going to be Gaussian, right? And they're going to concentrate at a rate that depends on the second derivative matrix of that loss and the learning rate omega. So here in this little infographic I've built here, my loss minimizer is theta2 equal theta1 equal the origin. And so what you see is that those credible sets, as the sample size increases, is shrinking around the origin. This is, and the way it's shrinking is roughly at rate given by that quantity there. So what does this mean? This means that the rate or the width of those credible sets I showed right here in this plot, the width is determined by that little fella right there, that quantity. Okay, so if I build credible sets, what does this mean for the behavior of those credible sets? Basically, it means that the frequentist coverage of those credible sets is actually not going to be the nominal level in general. Because we know that in general losses, in order to have confidence sets that have the correct width, the width of those sets has to be determined by the so-called sandwich formula. This is the sandwich formula right here in that middle piece, which basically says that I have two pieces. I have the bread on either side, right? And I have this meat in the middle, which is the variance of that gradient. I don't know about you, but when I eat sandwiches, generally they have more than just meat on them. It's a pretty boring sandwich. And this is kind of boring in that sense. So right away, though, you kind of see that generally Gibbs measures, Gen Bayes is probably not going to have the correct level of coverage unless we can somehow choose the learning rate to match the width of those intervals. And you might ask, is there any hope for this? Well, it turns out there actually is. In some cases, we're going to be able to choose the learning rate so that the generalized information matrix identity holds, which basically is that equation I've written there in the fourth bullet point. One interesting case where I've seen this recently, where this happens, is there's this paper from Tommaso Rigone and David Dunson, and I apologize to the first author who I never remember their name. I've read that paper like 3 or 4 times, and so I want to apologize. But basically what they show in that paper is if you use a quasi-posterior or a generalized Bayes posterior based on a GLM that has the first 2 conditional moments correctly specified, then the generalized information matrix identity holds, and you get posteriors that actually have correct coverage. That is quite useful, I think, because basically says if you're doing GLMs, which lots of people do, you can do them in a generalized Bayesian way and get correct coverage, well-calibrated intervals. Now, I don't want to talk a lot about this, because indeed, this is, I think, going to form the basis of a lot of Ryan's talk in 2 weeks. And so I don't want to steal his thunder either, but I felt like I had to mention it just to kind of maybe set the scene a little bit. The only other thing I will say about this is that there might be a way around this oh, well, there is a way around this if your loss is smooth enough. Essentially, all Gibbs measures do is they're conducting inference on a population loss minimizer. There are ways of transforming that loss when your loss is smooth, such that you can conduct well-calibrated inference on this loss minimizer, but you need the loss to be relatively smooth and relatively your parameter space to be relatively low dimensional. If you have both of those, then you can do this sort of transformation I've proposed in this paper, and you can kind of deal with Gen Bayes without having to learn that learning rate, essentially. But that doesn't work in every situation. In other situations, you're going to have to learn via tuning the learning rate, which, again, I think Ryan's going to talk about. Right, so backing up, what's our brief history of BVMs? And really, by our brief history, I really mean mine. I used to think of BVMs as kind of this tool that we used to say to the frequentists, ha, I can do everything you can do, but better. And then I started studying them in depth and went, oh my God, I'm so stupid. This isn't going to be the kind of panacea I was really hoping it would be. So long as, that being said, you can still get some very useful answers here, but you have to do this additional step where you tune the learning rate, essentially, to give you something meaningful. So it's a bit of being overzealous on my part, I think. And I would say this is probably the newer view of BVMs, is that they're not really giving us the same thing that we thought they were 30, 20 years ago. They're really just another way of thinking about the regularity of these objects and thinking about how to maybe correct their coverage or correct their by tuning the learning rate to make them agree and have reasonable frequentist properties as well. So I spent a lot of time talking about concentration and learning rates and everything else. And so the last topic I want to ask is I kind of want to take a step back and ask, does it matter? Kind of see the theme of this talk, right? Does it matter? Why do I care? Well, it turns out that if your goal is maybe prediction, or you're interested in the functional of the parameters, you might not care about BVMs. You might not even care about the learning rate, actually. And we've actually already seen this phenomenon a little bit earlier. So here's exactly that same plot I showed you earlier. I just kind of stripped all of Jay's notation out from it on his earlier slides. This is, again, that safe Bayes paper from Grunwald and Van Oben. We're looking at the squared risk of different Bayesian estimators and different generalized Bayesian estimators based on different learning rates. Each of these curves represents a Bayesian posterior, a generalized Bayesian posterior with a different learning rate. And what you see down here in the dotted line is the true regression function, actually. And what you see is basically after about 200 observations, the choice of learning rate doesn't matter. What's really important for the accuracy of those predictions is then the pseudo-true value, or the kind of risk minimizer that the model and loss in conjunction define. So this is a general phenomena, actually. So here I have a bunch of different plots, and let me explain exactly what they are to you in piece by piece. In the top right, I have the total variation, top left, I have the total variation distance between an oracle predictive. So there's some deity, it comes down and gives you the best model from your class of models as defined by some given parameter value. And you instead, what you do is you say, I don't want that. I want to do a power posterior, or I want to do a generalized posterior with a given learning rate. And the values of the learning rates indexing those predictives, are given by the x-axis here. And I have different sample sizes. And these plots are due to Jan. So thank you to Jan to making some lovely plots here for this paper. And what you see if you just look at this top left-hand corner is that for small sample sizes, it indeed looks like there's quite a bit of difference in terms of the different values of tau, giving you different predictive accuracy as measured by the total variation difference between my kind of oracle predictive and the corresponding power predictive. Now I've scaled these things up by root n because they're all actually collapsing to 0. We had to do it otherwise or else it didn't work. And what you can kind of see is across different types of losses. So this is total variation distance in the top left. Top right is KL divergence. And in bottom right, I have the ELPD, which is an estimator of KL divergence. And in each of these cases, you see that there are situations where it's better off to choose a larger learning rate, actually, in the sense that I get a larger or smaller learning rate, in the sense that I get a lower total variation distance or KL divergence. Lower might actually be better. That is the safe Bayes effect. That is what Grunwald and Van Omen called the safe Bayes effect, where possibly choosing a learning rate less than 1 gives you some inbuilt robustness to misspecification. But what about larger sample sizes? Well, if I look at the largest sample size we have, what we basically see is after about 0.01 in all, so choosing a learning rate of about 0.01, 0.1, excuse me, in all of our examples across all of these losses, it doesn't matter for determining the accuracy of your predictive. i.e., if I take a learning rate of 1 or a learning rate of 10, if my sample size is large enough, the posterior predictive that comes out of that is going to be indistinguishable between those two values. And its relationship to the oracle is going to be exactly the same. That is, if I think about the distance in either of these distances between the oracle predictive and the power predictive based on tau equal 1 or tau equal 10, the difference between those two is exceptionally small. So small that I have to blow it up by root n or n for it even to show up. And you might be saying, well, why is this happening? It's actually happening because of posterior concentration, which ties this whole thing back together. Because the posterior is concentrating, the amount of mass I'm assigning to balls around that oracle point in the parameter space is getting smaller and smaller. So that if I scale those balls up by some constant or scale them down by some constant, that constant's almost irrelevant in terms of the behavior of the predictive itself. More generally, if you think about building a posterior predictive based on some model, f of theta, where I integrate that predictive based on some Gibbs measure with some learning rate wn, then so long as the learning rate is not very, very small, if it's in fact the same order of 1 on n, this won't work. But if this is the case, then basically, on average, the total variation distance between the oracle predictive that you could possibly get and the power predictive based on a given learning rate is upper bounded by the rate at which that posterior concentrates. So think about what this means. This basically says that in large samples, so long as the learning rate doesn't go to 0 too slowly and the learning rate is bounded by some positive finite constant, then the difference between the oracle at two different learning rates that are relatively far apart is minimal, i.e., there's not really an optimal value of the learning rate. This isn't necessarily something that shouldn't necessarily be obvious, right? So if you look at this plot, which was, 2017, I think is when this paper was published, the phenomenon is right there. It was already hitting us in the face. We just didn't know how to put the math around it to say what exactly was happening here. But with the mathematics of posterior concentration, we can. And we can say if your goal is essentially functionals of the parameter and not necessarily inference on some parameter itself, like prediction, then choosing the learning rate is probably not going to kill you, essentially. Now, there's a kind of a darker side to this, though, which is that the learning rate doesn't help you either. So what this means is if you're thinking about the actual coverage of that posterior predictive, the coverage of that posterior predictive is tied then to the coverage of the oracle. And so if the oracle has bad coverage, then so is the power predictive. So it's a dual-edged sword here in a sense that, yes, the learning rate may not matter, but if you have a bad oracle, well, then there's not much you can really do about it. Okay, so it's kind of a dour note in a sense to end on, but it's just kind of hopefully more fodder for you to think about. So before I end, I kind of want to maybe circle back and address maybe why I thought this was a useful topic to touch on, other than Jeremiah's asking me to talk about it. I had to think about why we should really be interested in studying this. And I kind of was reading some quotes on statistics for a PhD unit that I'm doing at Monash, trying to get people interested in statistics and why we study it. And I came from a quote from Carlisle, which was kind of not about asymptotics, but about statistics in general. And I thought about where asymptotics sits in this. And what I've kind of come up with is that where we use asymptotic analysis and theoretical verification of the behaviors of these things is not really for understanding any given phenomena in particular about some problem at hand. It's really about not stepping on hand grenades. What I mean by this, it's about saving ourselves from the absolute embarrassment of believing in easy facts that are ultimately verifiably false. By having to think hard about choice of prior, what that choice implies for the behavior of the posterior, about losses and what those choices of losses give us in terms of concentration and asymptotic phenomena, we can quickly cut out lots of different losses and priors one might choose. And so it's not so much about an answer to a specific question, but about how to think about Gibbs measures more generally, I think. And I think I'll go ahead and end on that point. Thank you for tuning in. I'm happy to take questions now.
Brilliant. Thank you so much, David. Yeah, if people do have questions, we'll prioritize people putting their hands up first, maybe. Otherwise, we'll turn to the Q&A. Maybe while people have some time to think about it, I selfishly have one, David, if that's okay.
Oh, please, Jan, go ahead.
You mentioned briefly that sometimes we need the BVMs on top of the posterior concentration to be able to prove some sort of superiority of one method over another. And I was wondering, just because we showed obviously this predictive stuff just for the concentration, what are the instances where we need the BVM on top of the concentration, and what does that kind of look like?
I mean, so like I said, in my opinion, this is probably a bit biased, but really the reason we gave two stuffs about BVMs was so that we could tell the frequentists that we were doing the same thing as them. In my heart of hearts, like that's the reason why I think BVMs were developed in a sense, is to basically say like, look, I can do everything in this very coherent, useful way of thinking about it. And asymptotically, you and I are going to agree. And so my prior doesn't really matter so much. Now that's a bit jaded of an answer, and a more possibly realistic answer is that I need BVMs to really think about the repeatability of these objects. And when might the repeatability matter? The repeatability might matter if certain assumptions in my underlying framework are fragile. And so if those assumptions are fragile, well, then the BVM is not going to correctly calibrate. And you're going to have to think hard about how to make that framework more robust to those fragile assumptions.
All right. Bro. Okay, thank you. We have a question from Jeremiah.
David Augustin is raising his hand. So let's ask David first, because I speak with David Frazier all the time.
Okay, terrific. I'm muting you again, Jay.
Thank you for letting me go first. I'm really great lecture. Thank you, really interesting.
Oh,
and I just want to start by saying that I'm relatively new to this post-Bayesian field, and but I'm really passionate about Bayesian inference in general and sort of quantifying uncertainty and so on. And Jeremiah has mentioned in last week's lecture that, or 2 weeks ago, I can't remember, that sort of one of the motivations of doing post-Bayesian inference is sort of to deal with model misspecification, among other things.
Yep.
So now my question is sort of relating to these asymptotics. Maybe I'm a little bit critical here, but sort of my takeaway from this is that, okay, if for sort of at a certain amount of data, everything converges to the same posterior distribution, essentially doesn't that tell us that we're sort of still making the assumption that the loss minimizer, the set of Moslem defines as a model which should describe the data generating process in some way, and thereby doesn't actually help us overcoming this model misspecification issue?
Yeah, I mean, this is fundamentally correct, I think. At a philosophical viewpoint, I agree with this entirely. Right. So this is where things like coarse and posteriors come in. I didn't talk about coarse and posteriors, but you can think of coarse and posteriors as basically laying a prior down on the level of misspecification that never goes away. In fact, in the coarse and posteriors, what essentially happens is your posterior doesn't concentrate onto a singleton. It concentrates onto a set. And that set is the values under the prior that make that loss smaller than some threshold. Now, the only difficulty with this, and I come from a background in ABC and approximate Bayesian computation, is that you then have the question, just like in ABC, of how small do you take the tolerance? There's no clear answer to that, right? Mm-hmm. If there exists a singleton that makes it small, that's best, then you're back in the same thing. You're back in exactly the same framework. And so this isn't a criticism of the coarse and posterior at all, because I think it's a really useful idea. It's more so just saying that there's an equivalence there. So if you concentrate onto a set of loss minimizers, you have to define somehow how big that set of minimizers is. I fully agree with your point, right? I think if there's a way to not let the posterior concentrate when the model's wrong, but let it concentrate when the model's right, I think the first person to do that is gonna earn themselves something nice.
Okay, thank you.
Jay, do you want to go now?
Yeah, sounds good. Thanks a lot, David. I mean, we've worked a lot on these terse technical problems, and so it's really useful, I think, for anyone who's ventured down these dark alleys to see the kind of meta level of this research and kind of almost the culture behind it. So in you with that, I want to ask a question that isn't technical. It relates to a finding. You remember, this is like 2 years ago. So for those of you that weren't present in my meetings with David, we derived a really weird concentration result where essentially a posterior concentrated like a Laplacian, and not like a Gaussian. And I was wondering, in view of what you've talked about today, what can this tell us? Does it tell us anything?
Yeah. I mean, so the funny thing about that Laplacian, right? So basically, this was like a loss based on the Wasserstein one, right? And the Wasserstein one is sharp, basically has sharp corners, right? It's an absolute value function. And you could basically show that in that context, the posterior you got looked almost like a witch's hat. It didn't look Gaussian. It looked Laplacian almost. And basically, my reasoning for why that happened is basically you didn't have this second order expansion going on. You had something that was like the projection onto a specific surface, and that projection just happened to turn out to give you a loss, or to give that projection just happened to turn out to look a bit like an absolute value function, but inverted. And so when that happened, you got this very kinked loss, right? And so that projection, the posterior, when I exponentiated that, then looked exactly like that Laplace. That is a fundamentally bizarre object, and I've never seen anything like it. So weird that we didn't even bother writing it up because I just thought this was just an ugly thing, and I didn't even know where to even philosophically think about this. Because in both those cases, in that case, it's still not going to have correct coverage. Its credible sets are going to look like a Laplace credible set, which is not elliptical. It's going to be kind of brackety, I guess. I don't even know what that looks about. How to interpret that. I mean, it's not really an answer to your question, Jeremiah, but like it's.
Yeah. I was wondering if it tells us something, but I guess what it tells us is that a concentration result in itself is not necessarily useful, even if you get a distributional component to it. You really want the Gaussian. You really want the Gaussian, I guess, because it is intimately related to a squared norm geometry on the parameter space, right? And it's just an exponentiated negative squared norm. And so what you're saying is that Wasserstein induces a different geometry on the parameter space, and you get weird stuff. So it's kind of interesting because it imposes an implicit restriction on what kind of losses you would actually want to deal with as well, I guess.
But I also think that's because implicitly we have in our heads that we want correct coverage, right? And therefore, the Gaussian is kind of the one that gives us the correct coverage. If you don't care about that, if you just care about having not exact coverage, but necessarily you don't care about under coverage, right? If you're fine being higher than the 95% level, for instance, then other geometries might be very useful. There's a paper from Subashish actually, where he derives this BVM for specific classes of semi-parametric models, and it's not Gaussian. You can show it's not Gaussian. But you can also show that its coverage is only mildly larger than the nominal level. To me, that's better in some sense because I'm no longer relying on the squared geometry, essentially. So I think that's kind of another avenue of the philosophy behind this, that really there's not one size fits all here. We talk about the Gaussian because it's easy, in a sense, not necessarily because it has any holy sanctimony or something.
Thanks a lot. I'll end here, and then maybe we can take one more question if someone has a question remaining.
Oh yeah, Umberto talked about the paper from Henry and Yucca. I haven't read that one, but it's definitely very interesting. I saw the archive about it on the links between ABC and generalized Bayesian inference, but I haven't had time to read it, so I'll give that a read. Thanks, Umberto.
Brilliant. Otherwise, thank you very much again, David. And just to again very selfishly remind people that we have a workshop and to please register. thank you again, and we'll see everyone in a couple of weeks' time.
Thank you all for coming. Cheers.